Yes.
Yes.
Very good. Only one slide or two slides?
Just one.
Just one. That's enough for one day. Are you ready? I know we have still a few minutes left. Any question from the last lecture? Let me just put my screen that you can see me. Any question from last lecture?
Yeah, maybe not a question, but I don't know. Did you check the chat I just sent you? If it would be possible to do a quick presentation, well, not presentation, but announcement for a next week event of the ASHRAE.
When did you send it?
Now it's in the
Okay.
chat. I send it to you.
Okay, please, anytime, no problem.
Okay, so well,
Would like to do it
it
today?
just takes 5 seconds. Basically, I'm the ASHRAE Concordia Student Branch VP event, and we are hosting some webinars, monthly webinars. And there's one next week about building automation systems. I just put in the chat the link to the Facebook page and the registration form. So hope to see you there. It's a very interesting topic. So
Excellent. Are you interested to attend any meeting that, because I receive a lot of web email these days about the different subject about the building and energy and so on. If you're interested, I can also email you all of this when I get, every time I get.
why not? These days, you know, emails, it comes.
Now I can forward it because I receive a lot of different subjects these days. Everything become on computer, therefore it's much easier to attend rather than traveling to go into another city. Anyway.
Yeah, great, sure.
Yep. Okay, let me start. I do not know which chapter you are. Hopefully you're chapter 4. We finished chapter 4 and we will start at chapter 5. And you can see here is they're showing about the numerical method in heat transfer conduction. Believe it or not, you have been already using numerical technique. You use it in building science to calculate the temperature distribution in the wall, and you did it unintentionally in your project number 1. Therefore, more or less, you're familiar with numerical technique, but we are trying not to apply to case of transient. Therefore, the objective of this lecture, this chapter here, to understand the limitation of analytical solution of conduction problem and the need for computational technique, or we call it numerical technique. Because most of the problem you get so far, you have been able, as part of EMAT or here, to develop a sort of simplified equation. And in order to develop that simplified equation, we made a lot of assumption, okay, a lot of assumption that, and then we were able to apply for that application. Here we are trying to find out what are the limitations and trying to expand it for other application. In all, if you remember again, in chapter 2, we wrote the energy balance for a control volume in finite difference formulation, and then mentioned let delta x and delta t goes to 0, and we changed the finite difference formulation to derivative, okay? And we solve, we can, when we use this technique, numerical technique, we can apply to one-dimensional, two-dimensional, any three-dimensional problem in using finite difference method. We are going to describe what that means, finite difference method, and so on, okay? And solve also this other application, because we are not only concerned about the dimension, x of y and z, but also we are also look at the time, how we can march through the time, okay? If I answer for now, at the temperature at the surface of the wall is 10 degrees, how can I calculate the temperature 1 hour from now or 2 hours from now? Therefore, I will go march through the time, okay? This is the focus of this chapter, okay? Therefore, we are going from a steady state to transient. We are going to change now also through the time. If you look at it in chapter 2, we look at the we solve the different type of problem for different geometries, cylindrical, spherical, Cartesian coordinate. And what we did, we wrote a simple energy balance, and then we measured delta x and delta t equal to 0, and we were able to find a sort of a solution that we can able, for example, in the case of a spherical coordinate, we end up this equation, and then we measure the boundary at what is the temperature at the center, what is the temperature here. We use these two boundary conditions, we were able to find that a sort of temperature at any point in the sphere, okay? And then we were able also to calculate how much energy has been transferred, because now I know the temperature distribution. That if I use a Fourier equation, I get the derivative of this one at x equal r, and we find that energy exchange. Therefore, we develop a sort of a differential equation by performing a simple energy balance to do this one. Okay, we took a control volume and we wrote the energy balance, and we developed that one. And then we express the boundary condition I mentioned at x and r. Okay, therefore this was from here we got to here, and then we solved the problem differential equation. Therefore we took a control volume, we wrote the energy balance. Therefore that was the first part. We developed a differential equation here, and then we expressed the boundary condition, and then we solved it, and we were able to find this answer. But what is the limitation? Yes, we end up this one. This is a very nice exercise, and we did it, and this only we considered was about the function of r. But what is the limitation? We simplify the problem, okay? We simplify the problem that, for example, on the temperature we know on the surface here, okay? For example, we said, okay, let me know the temperature at the surface, and we were able to solve the differential equation. If the temperature at the surface is not given, and given as a function of the energy exchange by radiation, I cannot find any solution because I do not know the temperature here. Therefore, I have to go further with more complicated geometry. The geometry must be such that entire surface can be described mathematically. For example, I know I can define this geometry mathematically. This is a cylindrical system. Therefore, I know this r at r equal r, here is the surface, and r equal r is here, at r equals center here. If it has to fit exactly to the coordinate I'm trying to solve the problem, okay? And even this for the simple geometry, heat transfer problem cannot be solved analytically if the boundary conditions are not sufficiently simple. If I mentioned, as I mentioned in the previous slide, if here I mentioned there's no radiation, but if there's exchanging radiation with the surrounding, I do not know the boundary condition here. Therefore, probably I can solve that problem, but it becomes much more complicated, okay? Therefore, we always find analytical solutions, but analytical solutions are limited to the problem that are simple or can be simplified with a reasonable approximation. Every problem we solve in chapter 2 and 3, we try to specify exactly the assumption that you are making, okay? Based on those assumptions, we were able to solve that problem and find the temperature distribution in the body, okay? But how about this geometry? If I'm trying to do this one, if it's an egg, I'm trying to find energy exchange between egg and surrounding. I cannot find any system that describes the geometry of this system. I can simplify to come to this scenario and say this is a spherical system, but this is different from here, okay? Therefore, that's the difficulty that I will find it here. Yes, this is spherical. I have the solution for different boundary condition, but this is a oval shape. Therefore, that's difficult to define exactly the geometry on any system, Cartesian, cylindrical, or a spherical system. Therefore, we have to try to use a sort of another technique that we call a numerical technique to be able to find this temperature distribution in the system like this, okay? Therefore, there are complications. And for example, even if I can calculate the problem easily for here, that we did it in chapter 4, It's the difficulty here is we end up with this answer. This is, yes, we develop an answer, an equation for it, but again, every time you have to look at the special function and trying to find the eigenvalue and trying to look from here to infinity. Therefore, that's again, yes, we can do it, but it is very complicated. And every time we have to do this calculation. Therefore, the whole idea here is how we can find the answer for this complicated geometry or when the boundary condition is different, okay? If you recall in chapter 2, we wrote a sort of, when we wrote the energy balance, we said that we would like to calculate the temperature distribution in this body.
Sir, could you please go back to the last slide?
Yes, sir.
Thank you. All right, I'm good. Thank you very much.
Thank you, Peter. If you remember chapter 2, when I calculated temperature distribution in a solid body here, we wrote a control volume. This is the red control volume. And we wrote energy balance of this control volume. Conduction comes in, conduction leaves, and there is an internal heat generation, and there is some energy storage. For rate of conduction at x, rate of conduction at x minus the x plus delta x, how much energy generated in the system here, and this change in temperature of the system as a function of time, energy storage capability of okay? And that's exactly the Qx come in, Qx plus delta x leaves, energy generated here, and here is a change in the temperature of the system as a function of the time. This delta T here. And then we mentioned that the replacement here is we use table expansion, and that we did it like this, and we wrote it like this. This is we replace this 2 minus this minus this, and Q delta x. I'm sorry, this is show here again. This was energy difference. Let's move to 0, okay? Therefore, if delta x and delta t go to 0, we end up with this differential equation, the answer here, okay? Therefore, we make from here to here, we mentioned, let's this move closer to 0, and this goes to closer. Therefore, this difference becomes differential equation here, and we were able to find it. But we don't want to do this one anymore. We said, let's stick with this equation that we have here, okay? Let's forget about this part, and let's stick here. Now, so look at the delta Q between these two points, and delta temperature here. Therefore, we are not going to transfer it to differential equation. We look at honest difference that we have here, okay? Therefore, we're talking temperature 5 minutes from now to temperature now, divided this delta 5 minutes, and here the delta Q that passed through this delta X thickness, okay? Therefore, we stick with this part. And therefore, we are going back to one dimension to trying to develop technique. Believe it or not, as I mentioned, you have done it already. What we do, we discretize let me go back the difference between here, let's stick here. We discretize the wall, okay? And they're trying to find the temperature at every point that we are interested. Exactly the way you did in building science and exactly in project number 1. And you take a control volume here, this is your control volume, and you write the energy balance for this point, okay? I mentioned now my delta x is 5 centimeter. It's not going to 0. It's going to look at I want to find this one between this point and this point, and between this point and this one, okay? Therefore, we discretize the wall in the number-wise point, 5 points, 10 points, 100 points, depend on the level of accuracy that you would like. And again, we ignore now the energy stored in the system. Again, we write Qx come in plus Qx plus rate of energy generation is equal to 0. That's exactly fine, okay? Again, as I mentioned, we write to the point. Energy comes from this side plus energy comes from this side, and that's node M. Therefore, there's conduction from M minus 1 to here and M plus 1 to here, and plus energy generated inside this delta X control volume, okay? Therefore, we end up with this equation, okay? And we know what is energy generation. Remember, the thickness of this slice here that you have is delta X. The surface area is A. And that was energy generation, this control volume here. And then the conduction comes from this M minus 1 to M, exactly the way you did in project. From M plus 1 to here is equal to 0. Therefore, we have all those equations that we have. Remember, again, we are writing here the energy balance between these 2 points. This is m minus 1, this is m, and here. Conduction from here to here, plus conduction from here to here. Okay, that's exactly, we did it last time. And the distance between m and m minus 1 is delta x. The distance between m plus delta 1 is delta x. Therefore, we take half of this between these two and half of this. Therefore, this region here represent node M. Therefore, the whole this, we assume this slice here, this control volume, the temperature everywhere is Tm, okay? Keep in mind, therefore we write that equation and we end up like this. Therefore, we can write conduction from this, conduction go from here, plus heat generation is equal to 0. This is exactly the equation that you had before. Now, if you have heat generation, you can add also heat generation. If you don't have the generation, exactly this become you have here. Conduction from here to here, conduction from here to here is equal to 0. Therefore, you don't have this term here. Therefore, now you have used this technique before, but now we are going to explain step by step, okay? Therefore, when we mention here, you discretize this node to M node from 0 interior surface, M outside. Therefore, from node M to node M minus 1, you have M minus 1 equation. You write one equation for here, one equation for here, and this is here. Therefore, you have, for these are, we call it interior node, inside the wall. This one, and all the way to M minus 1. Therefore, you have M minus 1 equation, okay? Therefore, equation is applicable to each node of M1 because interior node here, interior node, and it gives you M minus 1 set of equation. But in reality, you have M plus 1 because you do not know this temperature, 1, and you do not know this equation here. Therefore, you have to write also equation for this node and this node. Okay, we call it this surface node. Okay. Therefore, you have to write 2 for the boundary condition that you have. Okay, this is for interior node, conduction from here to here, conduction from here, and plus heat generation for 0. Okay. Therefore, you end up with M minus 1 because you have M node. If you have 10 node, you have 9 equation unknown plus 2 boundary quota here. Then you start to write it down, okay? As I mentioned before, we always use this scenario. This keep us sort of consistent throughout the equation, that we can look at the equation and say, okay, this equation is correct, okay? Because if you write like this, it always go to this one, it goes to this one. Always the term representing at the node T2 is this become negative and this become positive. Or as long as you be consistent and for all the nodes, node number 1, number 2, number 3, node M, right, this comes in and this leaves. As long as you are consistent, you have no problem of visualizing and being able to explain your equation correctly, okay? And for either case, if you write this one or this one, your equation, the equation that you are writing the formula, this become negative, this become negative. You are writing for equation for number 2, therefore the coefficient here is -2 and -2 here. And that shows that all the term in diagonal of your matrix is negative. All the term, the coefficient is negative, okay? The other 2 is positive, this one and this one is positive, the diagonal is negative, okay? Therefore this, you have done it before, and I always recommend, right, energy comes in plus energy comes in is equal to 0. Therefore, you can write your energy balance without zero. So far, you did not have an internal energy generation, but if you have internal generation, you can add it to it, okay? In this case, assume that you are having, for example, like pouring concrete. Any question, please? Now, the question here, remember, we discretize equal distance. The distance between this one and this one, delta x, from here to here is delta x. And this boundary represents this node 2. How we do it? We take half of this one here, we call delta x over 2, and delta x over 2. Therefore, this is from here to here, delta x over 2, delta x. Therefore, the thickness of this layer is delta x, okay? As long as interior, we have no problem. When we come sort of at the surface, assume that you're writing equation for here in the surface, assuming if you have a heat generation. Now this equation, when you write the volume, you have to consider this half of them, because this line represents between this one and node number 1. Therefore, here is node number 1, here is 0. Therefore, you put the boundary between two halves. Therefore, this portion represents node number 1. And when you're trying to calculate the energy generated for that portion, is we have to keep in mind is delta X over 2. Okay, keep in mind when you're writing the energy balance for node number 1 or number M here, keep in mind the thickness is delta X over 2. Okay, when you're considering energy generation. But it's still, the distance between 0 and 1 is delta X. This is remaining the same, okay? But only this part is generated. Over here is the boundary node. There are some energy comes here, heat flux comes here. This is this one, plus some conduction from node number 1 to 0, that this one, and there are some energy generated here. Therefore, this gives you your equation. But keep in mind that the portion that generate energy is delta X over 2, because only half of this belongs to node number 0. The other half is belong to node number 1. Okay. Any question, please? Okay. Again, when you have two material connected to each other, that the case that you have, for example, in your project, you have material A, material B. Again, when you discretize, you've mentioned this is node number M, M minus 1, M plus 1. When you're writing for number M, that shows the interface. When you are writing, for the conduction doesn't matter, because conduction from M minus 1 to M is this one. Conductivity of A, conduction from B, M plus 1 to M is B. But when you would like to write for energy generation, half of them is generated node I. This is exactly here, delta X over 2. The other half is generated by material B. Okay. Therefore, you have to keep track of the thickness of material when we are involving with energy storage or heat generation. For conduction, it doesn't matter, because we discretize, the distance is always delta X from here to here. From here to here is conduction. Therefore, to this surface here, and here is delta X and delta X. Okay. Therefore, here when we write the energy balance, come from M minus 1 conductivity A, from A plus 1, M plus 1 conductivity B. The distance is delta X. Energy generation in control volume A is from here to here is M. From M to M minus 1 is delta X. This thickness is delta X over 2. We are right here. And the same thing as I mentioned is half of this thickness considered as forming for node number M. Okay. Therefore, here this section represents node number M. Okay. Therefore, that's we have to keep track of. And if you write it for boundary condition, and outside, again, the same value here, you have solid material K, the conductivity K, and here you're exchanging energy with the environment, and you're exchanging by convection and by conduction, but your material is also generating some heat, okay? Therefore, you write conduction, you have convection coming here, plus long wave radiation, that comes here, plus conduction from this point to this point. Again, the distance between point 1 and 0 is delta X, the temperature, and plus how much is, what is the volume of material representing node 0, the bottom, this is delta X over 2, therefore this portion represents node number 0 that exchange energy with the environment. Any question? Okay, therefore you have seen them before, but we also adding some other aspect generation that in case you have dealing with a problem like that. But now we learn all of them for one-dimensional. The same concept can be applied to two-dimensional. Therefore, if you have dealing with a material like this, it's two-dimensional, therefore you can solve this problem. As long as you consider you have X direction, you have Y direction. So far we have only this direction, but now we have this. Therefore, you can start it from any node and start write the energy balance for every node. and then you have m node, m unknown. You can solve the problem, okay? Therefore, you have two-dimensional, this size representing m, this representing n, therefore is Tmn. Therefore, here, this temperature need two reference coordinates to show them, m and n. M is representing x, n representing y. For this node here, m plus 1. Node here is n minus 1. Therefore, you need two-dimensional. Therefore, each node needs two coordinates to show them x and y. Okay. Therefore, you can write energy balance for every node and that numeric equation that you may have. Okay. Therefore, that's we can apply whatever we know already to case of geometry that's not really well defined. Okay. Therefore, you can take any geometry and write, consider one-dimensional, two-dimensional, and solve the problem. Okay, based on simplifying the concept by discretizing the geometry, and then either one-dimensional or two-dimensional, write the equation for each node. For each node, you can write the equation and solve it. Any question?
Sir?
Yes, sir.
So -1 or +1 is
we have
that we consider that we have to set up ourselves when we
No.
divide the area by a certain amount of let's say squares or units.
No, let me explain it again. You have a geometry like this, okay? Therefore, this is two-dimensional, x direction and y direction, okay? Now, I only select portion of the whole geometry. Assume your geometry is this one, this part, okay? And you would like to calculate the temperature in every point in this portion, okay? Right? This is x equal L, and this is y equal D, okay? Therefore, it's a two-dimension. And I ask you to calculate the temperature of distribution in this geometry. In this case, it's just a simple rectangular, okay? Therefore, you have to discretize the system, okay? Discretize the system, therefore, you mentioned you are selecting, for example, here is 20 centimeter. We divided this one, let's say, to 21 centimeter distance. Therefore, here is 0, here is 20. Therefore, you have 19 point in between. And you have discretized this direction, let's say to 30. Here is 0, here is 30. And you did it at every 1 centimeter. Therefore, here is 0, and so on. Therefore, you have 20 times 30, 60, 600 nodes, okay? And let's say this is only portion of that I show you in this plate, okay? I put it in general term, M and N. This could be probably 15 and 16. Temperature of 15 right here. This is node 15, and here is 16, okay? Therefore, you have to discretize the geometry you would like. And here is only showing you a portion of this plate that you're trying to get. We do one problem next lecture, you will see it, how it works, okay? And for what you have to do first, you have to discretize the system and trying to find how many temperatures we are interested to find, okay? Did I answer your question, sir?
That's what I was saying, but so basically, yeah.
Okay, good. Therefore, for example, here that you're trying to look at for temperature over here, you write conduction from this node to this node, conduction from this node to this node, conduction from this node to this node, conduction from this node to this node. Therefore, you are right here, this is conduction in the M direction. It means in this direction, X direction. This represents the conduction in the Y direction, plus energy generated in this control volume that shows this right here, okay? Therefore, here now, rather than writing only one dimension, you have also conduction on the Y direction. Conduction from M, N minus 1 to M and N, conduction from N, M, N plus 1 to N. If you write it down and simplify the equation, that will come back to this. Okay? Any question? So far, we assume that's a steady state. The boundary condition does not change as a function of the time. The boundary condition remain constant all the time. But now we can look at another scenario that let's look at here. We have a problem one-dimensional, but also we're considering the time. We are only interested to find out how the temperature changes as a function of the time. This is time equals 0, and it's slowly 1, 2, and so on, okay? Again, we have to also not only discretize on the dimension here in y direction, but also we discretize in the time. Therefore, right here, I discretize in the length, the thickness of the wall. This is interior surface, this is exterior surface, and these are the points inside the wall. But also, I have to look at discretize to the time that we go. Now, 5 minutes from now, 10 minutes from now, and so on. Therefore, this represents the delta T. I'm interested to calculate the temperature every hour in the case of project. Therefore, this becomes 60 minutes or 3,600 seconds, okay? Therefore, I have to merge to the time also. Therefore, we write the same way we did it before. Energy transfer to the control volume and all the surfaces. It could be one-dimensional, it could be two-dimensional, it could be three-dimensional, the same thing that we did in the problem in chapter 2. Therefore, it could be different dimension. Therefore, we have to X, Y, and Z. We can write all the conduction going to that point, X direction, Y direction, and to Z direction. And if the system also generates some heat, we will include it. Exactly we did it before. Therefore, this is to the all different sides, X, Y, and Z. This is generated through the time, and this is change in the temperature of the system. Look at before this was delta over delta T, we multiply here by times delta T. Okay, this is the same as the equation that we had before. Okay. Therefore, basic here, we're not only on discretizing on the X, but also we are discretizing on time. And we select a time step. We call it time step. The delta T, the time step every 5 minutes, every 10 minutes. This is we call it time steps. Okay, and then we write the equation for every node until we have all the equations that we have. Okay, and for now your equation has been changed. In all the direction comes here for the X direction, Y direction, Z direction. Therefore, you write conduction to wall, X direction plus Y direction plus Z. If your system generates some heat, you also include this term. For example, I said in the wall, we are generating heat, therefore we multiply heat generation by that control volume that we have. And here it shows how the temperature of node M, here in this case, we have here, this node, the temperature change over a period of time. I'm writing equation for this node here, therefore represent here it changed through the time, okay? Therefore, here this is X direction, but at the time I, okay? Therefore here we are trying here to go to the next step. We're trying to find out if I know the temperature now, how can I calculate the temperature 10 minutes from now? Therefore this one would represent time step. Your delta T could be 10 minutes, could be 15 minutes, could be 1 hour. Therefore this represents time step that we have here, okay? At this time, I represent now, and this I plus 1 is the next time step. Then so because the same approach that we use, the same equation we saw in chapter 2, end of chapter 2, we have this set of equation. Conduction from all direction, generation, plus the change of the temperature of that node over the time step delta T. Okay? Any question, please? Any question, please? Let me go to the next slide. If we look at here, we can use two different techniques. Look at here. This minus this. Look at here. Ti is the time now. Ti plus 1 is in the future. And 1 does not represent number 1. It represents 1 delta T. Okay? Therefore, this mentioned now plus 15 minutes from now. Therefore, this represents how many delta T we are considering. Over delta T. Okay, this is the term we have here. Now, there are two techniques to solve this part of the equation here. We call it explicit method and implicit method. We use, the question here is, which one we would like to use technique, okay? One of them call it explicit technique, the other one will call it implicit technique, okay? If I write the conduction that I have here and energy generation that I have here, I said the conduction that I have here plus heat generation that I have here equal this one that I have minus this one. E plus I plus this one. Now, depend which one I write here is, if I would like to write in the future time step, conduction, if I know the temperature now, I know the conduction now, I know heat generation now, and I would like to calculate the temperature in the future, okay? This is one technique. Therefore, I know conduction now, I know heat generation now, I know the temperature here, I would like to calculate. We call it explicit method. And for the equation that you write for conduction, you write for the time now. I write heat generation now, and I would like to calculate the temperature in the future. Therefore, remember the terminology explicit method. When I write the conduction, I know the temperature now because I measure it now. Heat generation now, and I would like to look at the temperature in 10 minutes from now. Or I can consider for the future. I shall look at here. The conduction at that moment is that. Heat generation is that. The temperature is that. The only thing I know is the temperature now. Therefore, I use this temperature to calculate all the temperature in the future. Therefore, we have explicit technique and implicit technique. And we are going to use one of this technique to solve our project, okay? Therefore, do you have any question here? Here, if expressed at the I, we call it explicit method. This one at the I, heat generation at I, I'm going to calculate the temperature and fuel. The formulation of explicit and implicit method differ at the time, a step at which heat transfer, heat generation in terms expressed. Depend this one or this one. By using this one, now we call it explicit. If I'm going to look at future conduction, generation, and everything, and by using the temperature now, I call it implicit. Okay? So you're
question.
Yes, sir.
For the implicit method, the left side of the equation, they are all future energy.
Yeah, because this shows the temperature variation on the time step that I have the temperature at this moment, this one, I'm trying to calculate in the future. Therefore, I'm trying to find out how much energy has been stored in my material or released. Therefore, this will not change. But the question here is how to write your equation. That's the question. Here, we can look at here, I know everything now. I'm trying to guess what will be happening in the future. In this case here is, I know the temperature now. I would like to calculate everything in the future. Okay? This is the difference between these two techniques. Therefore, this is the technique that we are going to use it, okay? The question one way is easier because there is, again, when we break down this equation, we will see there are some constraint, mathematically constraint that we have to satisfy. For one case, we have some constraint. The other one, we do not have the constraint, okay? Just remember, again, between explicit and implicit technique. Explicit and implicit technique. This is the general equation that we are going to use here, okay? Depend how we write your conduction term, okay? Now, if you look at here, if you take this, again, wall that you have, one set of material that you have here, and only we are looking on the X direction, and this is my node number M, I would like to calculate the temperature at node number N. Remember now we are considering transient, okay? Transient, okay? The same thing, energy comes to this point, the energy comes to this point, plus generation, in your case you don't have generation, shows a variation of the temperature of node number M as a function of time. Therefore, you have conduction coming here from here, conduction come from here, this one, plus how much is energy generation. Look at here, this is interior node, therefore the thickness is delta X, and this represents the energy, the mass of the system. Rho, A times delta X shows the volume, times rho represents the mass, and that's Cp, and write this equation. If I simplify this equation, if I simplify the equation that I have here, I have Tm here, 2Tm, and so on. Therefore, my equation end up like this here. Therefore, all these are, I simplify them, put them together. This is energy generation, this one divided by K, and here, the right-hand side. Now I have a Tm here, right here, Tm here, Tm here, Tm here. Therefore, and if I simplify the term, my equation will end up like this, okay? Remember, I have alpha, I have delta T, I have the thickness that represents my Fourier number. This equation will be simply transformed to this equation I have. Therefore, that's exactly the same. The only thing, I put all of this quotation together, okay? Then I put them together, I will bring them one side and so on. This represents my explicit equation, okay? This is plus this one and this one, okay? Or if I take this Tm from here and put it the other side, I can calculate my future temperature here. Okay, here is my temperature at future time. I have tau, this Fourier number. This is my old time. This is my old time here. These are time at this moment. And this coefficient for Tm, I have 1 minus 2 times Fourier number plus this one. Therefore, equation here that I wrote it down here in explicit form will become like this. In explicit form. Therefore, I can calculate the temperature node number M in the future, knowing the temperature M minus 1 at the previous time step I, M plus 1 previous time step, M previous time step, and all the physical property dimension of the system. It look very easy. I can calculate Ti, just simply like that. But mathematically, there's a problem. Mathematically, if I want to solve this differential this equation here, this term has to be positive. This term has to be positive. Otherwise, my solution will not converge. Therefore, this is one of the shortcomings of this using explicit technique. But if I wrote the same equation that I have here, in the form of implicit, this is not anymore now, it is future, 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 and so on. Therefore, that equation will be transferred to this format of this equation. That I have temperature now, Ti, I would like to calculate M minus 1, and M plus 1 here. And there's no constraint here because this is 1 plus 2 Ti. This is positive, and therefore, there is no problem. Therefore, I suggest when you would like to solve your equation for your project, use it implicit. Use it implicit, you have no problem. You can take any time step that you would like. Any time step that you would like. Otherwise, if you would like to use explicit, you have to make sure this term is positive. And when you're trying to satisfy this condition, your delta T becomes 5 minutes, 10 minutes. And is not easy, okay? Therefore, in your project, please use implicit technique. Therefore, you can take the time step of 1 hour, calculate the temperature at 8 o'clock and jump to next time 9 o'clock, 10 o'clock. If you use explicit, it gives you a lot of constraint that you have to select delta X and delta T somehow that this term to be positive. And for this, you have some mathematical issue in this equation when you're trying to look at explicit. Any question, please? Any question, please?
Sir, why do we have to keep the 1 minus 2 tau positive?
Go back to numerical course that you take. Therefore, this is the coefficient of this term that you have. This mathematically, if you try, you can keep it as it is, but you have to satisfy this term to be positive. Otherwise, your solution will not converge. It means your temperature goes to minus 10,000 or plus 67,000 or infinity.
Okay.
Therefore, that's the problem of conversion. You have a matrix, and in order to solve that one, and your solution to converge, you have to make this coefficient of this term positive. If it's negative, it diverges, and you never get the correct answer. The temperature goes to minus infinity plus infinity. Okay?
Sir?
Yes, sir.
Can we, for a check, can we check if 1 minus 2 tau, calculating tau, is positive, then we use the explicit, or rather just use implicit directly?
You can use it, as I mentioned, you can use either of them, but you have to make sure the delta x that you select, the delta x is 5 centimeter, 10 centimeter.
Okay.
You can find from this expression here, in order to be positive, you specify your time step. If you use this one and say this has to be positive, and when you calculate, you said my delta x is 10 centimeter, and then they gave you the equation, how much should be your delta t? And delta t crop. Okay. And if you select that delta t and is smaller than value, your solution converge. If the delta t is bigger than that, will not cover. Okay, let me go to the next slide to see we will get it some part of here. I will explain it to you. Therefore, and that was for interior node. Therefore, this equation, and this equation apply from node number 1 all the way to m minus 1. Therefore, for interior node, since the delta x is constant, this equation is correct for every node, interior node that you have. Okay, for every interior node that converts. If you go to exterior node, it end up like this here, in the boundary condition here, and boundary condition here, you have convectivity transfer that you had it in project number 1. You have conduction from node number 1 to here. The only point you have to be careful is about the volume of this node. Because remember, you have a mass. Remember, you have a mass here. Okay. Therefore, in this case, you are only having delta x over 2. From here to here is 1. There's a boundary between node number 0 and 1, and this represents portion belong to node 0, and this portion belong to node number 1. Therefore, you're here, the thickness when you're including for mass become delta x over 2, and the portion including for heat generation is again delta x over 2. Okay, and for now you have this issue. Otherwise, the same thing happened for conduction and convection. You have convection, conduction. The only thing you have to keep track of the thickness of the control volume you select. The boundary here at x equals 0 is delta x over 2, and L is equal to x equal to. Okay, and for that now your equation will be transferred in this format that you find in. Okay. Now, if I go back, what we mentioned about explicit and implicit, if you use the form of explicit technique, okay, there is a limitation on time step that you select. Therefore, we have to convert. Therefore, you have a previous information you're trying to calculate the future one. Therefore, there's a constraint. As I mentioned, this term has to be positive. This term has to be positive. Therefore, it means your tau from here, this plus 2, it has to be positive. Therefore, you write it down, tau from there. Therefore, it has to be in this term. Okay. Therefore, tau has to be less than 1.42. And from here, when you're trying to solve here, you select a thickness delta x, and from here you calculate how much would be your delta t to satisfy this condition. And if it's in the boundary condition, you have to check also for boundary condition. Okay. Therefore, this in order to create some stability in your solution. Otherwise, your answer will oscillate up and down, and suddenly either go to plus infinity or minus infinity. Therefore, if the time step delta is not sufficiently small, this time step here, the delta t that we have, this is Fourier number, and in Fourier number we have the time step delta t. the solution obtained by explicit method may oscillate widely and diverge. Okay? Therefore, you will never get the correct answer here. Okay? Therefore, my suggestion is to use implicit, and therefore you can keep the same technique you used for project number 1, but here you have to modify your equation and integrate also the right-hand side, the term mass. Okay? Therefore, the same procedure that you used before you can do it, but use implicit technique, and only you have to modify your equation for every node and integrate also the energy storage. Any question, please?
Excuse me.
I'll go ahead. Sorry.
When we say delta T has to be sufficiently small, how small? Like, is it trial and error based on the situation?
No. Right here. It tell you right here. This has to be positive, and if you say positive, you will end up like this. Okay.
Okay, so we keep trying different intervals to see which one would be positive, and that's
right.
the number.
But
Okay.
the problem you have is, I'm not saying it's a problem. The solar radiation I give it to you is hourly. You know, at 9 o'clock, you know, at 10 o'clock. Okay?
Yeah.
But if you would like to, if you use implicit technique, there is no problem. You can take one hour time step. You calculate your temperature at 9 o'clock and then move to 10 o'clock. You have solar radiation at 9 o'clock, no problem. You go at 10 o'clock, you calculate at 10 o'clock. But if you're trying to use explicit technique and you do the calculation and you find your time steps cannot be more than 10 degrees, 10 seconds or 10 minutes, okay? You calculate at 9 o'clock and then you have to do your calculation at 9:10. And then you have to do the calculation at 9:20 and 9:30, 9:40, 9:50, at 10. Therefore, you have to extrapolate your radiation between 9 o'clock and 10 o'clock and create more work for you, okay?
Okay.
Understand my point?
Yes, thank you.
Okay. For the temperature, you have no problem, because for the temperature, you can calculate anytime you would like, because you have a curve. You can put 9:10, 9:15, 9:20, and so on, okay? And again, when you change the material, again, you come back here. If you change from mud to stone, your alpha will change. Am I correct? Because the physical property of your material will change, right? Therefore, you have to select for all different scenarios and find out the smallest one, because that has to satisfy all the equation, okay? Therefore, your tau here has to be a value that your time step delta T has to be a value to satisfy all the equation for walls, for roofs, and so on, okay? That's the problem that we have. That's why I suggest, in order to do that, use implicit, because then your headache will be less.
Okay,
Yes, sir.
thank you.
Delta time. Sorry. What's the units of delta time here?
It's a little louder, please. Say it again, please.
What are the units? What's the unit for delta time?
Well, I do not know. I just put the number here. I know what is the unit of alpha. I know the unit of delta X. Therefore, I can calculate what is the unit of delta T. Depend on the unit of the alpha that you use. Alpha, you have conductivity, you have CP, and you have heat transfer and so on. Therefore, you put them here. You have CP, rho, and conductivity. If your conductivity is watt, therefore your delta T become second.
Okay.
The unit depends what is the unit that you use for alpha. Okay. Therefore here, and therefore if you use conductivity is watt degree per square meter, your delta T give you the time step up in second. Yes, sir.
What's the name of alpha? Just how do we?
Thermal diffusivity, my friend.
Thermal
Diffusivity. And if you
emissivity.
diffusivity, let's go look at your table that you have. If you have your textbook, you open at the end.
I just don't understand the word that you're saying.
Somebody speak English. Mention what that means. If you look at in the back of your book, you have conductivity, you have specific heat, and also you have thermal diffusivity. Diffusion, remember?
Okay, perfect. Thank you.
And that's the unit is meter square per second. Therefore, that's the unit of alpha, because you have Cp, you have rho density, and you have conductivity. And if you look at chapter 2, when we write the equation, we define what that means in alpha. And mention is thermal diffusivity. And it's called diffusion, okay? Because representing two forces, diffusion by mass and diffusion by energy, okay? Any question? Therefore, if you would like to visualize it here, this is the trying to look at here. You would like to have this scenario times step number 1, the violation. It means this temperature will not satisfy the requirement that we needed. Therefore, it will go back and forth and usually go up and down. Therefore, that the temperature will never converge to the point that you would like to have it. Therefore, in conclusion, what that we mentioned, in conclusion that we mentioned here, what the rain is coming here is the implicit method is unconditionally stable. Therefore, you do not need to satisfy any requirement. Unconditionally stable. Therefore, you should not be worried about the delta T you have to select. But when you select here, is disadvantage implicit is that the result of the equation must solve simultaneously at each time step, and it has to be this term positive. Therefore, there is some constraint that we have to do it, and in this case, that we have to do that, okay? Therefore, in the case of implicit, you have no problem. You look at back here, let me go back here, look at here, the equation that you have here is Ti plus Ti, all of them at the same time, okay? When you write it down in this format, you know this time at the time step now. Here is much easier because you know this value, you're trying to calculate it here in the future. When it comes to the implicit, again, you do not know this 3 equation, okay? This is exactly he's trying to say here, okay? There is no issue about the stability of the answer. Therefore, you can select any time step. When we're trying to solve, you have to solve a set of equation simultaneously, the same way you did it in project number 1. You're trying to calculate the temperature at node number m, m-1, and m+1 simultaneously, okay? Again, the same format that you had it before, okay? You have to have n equation and n unknown, and you have to solve them simultaneously together. And that's the requirement, okay? This is the advantage. This, they call it disadvantage. That's why, okay. The reason they call it disadvantage, because in the case of explicit, you have only one unknown, but here you have one equation and 3 unknown that you have to do that, okay? Therefore, you can use the same scenario that you had before, but you have to make sure that you write down your equation correctly, okay? Any question, please? Any question? Here only, again, your textbook give you some example that how you discretize. For example, you have a wall here is a certain distance, then you're trying to look at, for example, here is 4 centimeter that you have, and you would like to calculate the temperature here, and temperature here. And you would like to select only one node. Therefore, you discretize here, and then your delta X becomes 20 centimeter, okay? 2 centimeter here, okay? 2 centimeter and 2 centimeter. And you write the equation for this node, you write the equation for this node, and you write the equation for this node. You will end up 3 equation and 3 unknown, okay? And you solve it. If you write it down in the form of explicit, therefore look at here, you have the temperature in future as a function of the temperature past time. I here, you calculate here. Again, temperature number 2, you calculate the temperature at the future 10 minutes from now, 20 minutes from now as a function of this one. Therefore, in both cases, you have to make sure that this term, the coefficient of T1 here, I, and the coefficient of the T2 represented here, this term has to be positive and this term has to be, therefore you have to solve it for here to find what is the delta T for this one, and you have to solve it for here and find out what is the delta T from here. And selected the smallest one to satisfy the scenario that you have, okay? Any question? Again, look at here, this is simply writing down for this part. And again, look at here, the delta X that we are considering. The thickness, only this region, red one, representing node number 2 for mass and also heat generation. Do you have any question about this lecture or about the problem that you have?
Sir?
Yes, sir.
Under the line of node 2,
Yes,
it's
sir.
still, is it the third node or?
This one?
No, under.
This one?
Yeah.
This one is trying to simplify this one.
Oh, okay. All right.
This one is a simplification of this one, and then end up to this part, okay? Therefore, this 2 step is getting to this part. Because here first, put in the conventional term that we have here divided by k both side, and then we're trying to simplify and mention, okay, this is representing tau, and this representing the other coefficient that I have. This represents this coefficient that we have, okay? And so that's, again, all of them is related to node number 2. Okay, therefore now you can start your project number 2, okay? And because please read the chapter. Again, the format, again, the same thing that we have done already. You follow the same discretization that you did for project number 1. At least select 3 or 4 nodes. And then complete your equation now by considering you have every node, it has a certain thermal mass. And thermal mass only represent, if it's interior node, is delta X times A rho Cp, that temperature of that point between now and future, okay? Again, let me go back here. Look at here. If you write here, the temperature between now and future. Therefore, you already have this side of the equation for assignment number 1. You have this side of the equation for number 1. You do not have internal heat generation. This becomes 0. Now this is not equal to 0. This is equal variation of the temperature of the mass as a function of the time. A times delta X represent volume, times rho represent mass, times Cp. Temperature of that node change over that time step that you would like to select. This one represents 1 time step, okay? It's not mean 1 second or 1 hour, okay? This represents the time step we call it. We call it time step. Time step if you use implicit technique, this becomes 1 hour. 3,600, okay? This becomes 1 hour, 3,600, okay? Therefore, you have to go back and modify all of your equation considering this component. But please, please, please be careful when you're writing for boundary condition here, your delta X is delta X over 2. Simply because here, delta X over 2. Simply because here is node number 0 and node number 2. 0, number 1. And we have to discretize, therefore there is a boundary between node number 1 and 0. What that means, it means this region that we consider. This is one of the limitation of numerical technique. We assume this part, all of them have the same temperature T. And all this part represent the temperature node 1. Therefore, there is a line between number 1 and 2 that shows which boundary represent number 1, okay? Therefore, at the boundary, we have always to keep track of the thickness of the wall we have selected. And if you have 2 material, you have to also keep track of that part, okay? For example, if you have 2 material, you have material mud and stone, make sure that your node, wherever your node it is, keep track of conduction from here, plus you have another term in the right-hand side that represent half of this mass plus half of this mass, okay? Therefore, your right-hand side here is the steady state, But in your case now, this becomes transient. Therefore, you have a term here that represents the mass of this part. It means rho A, XA times area times CP for material A, times the temperature here. But here is your delta X over 2. Remember, A times delta X over 2 times rho times CP for material A. And then plus this one. Therefore, when you have two materials going together, you have to keep track of them, both of them, okay? Therefore, please start to do it today or tomorrow or the weekend. And if you have any question, please do contact me, okay? This portion is a little bit tricky, and therefore need some discussion, okay? In that case that you had it before, you were going to the only 1 hour and finish. But now, if I use implicit technique, that I have here, TI of that node, you have to keep track of that. Because when I'm trying to calculate the future time, I have to know what is therefore at every time step, when you calculate at 9 o'clock, and you would like to move to 10 o'clock, keep record of all the temperature of the node at the time 9 o'clock, because you need it to calculate the equation. When you get calculate at 10 o'clock, this 10 o'clock node become the old time. Therefore, now you have to keep track of all the previous temperature at every time that you're doing. And when you start your problem at time equals 0, what is the temperature? Do you know what is the temperature inside the material at the time you start the first day? You know the temperature at the problem? You do not know. Therefore, we call it initial value. Therefore, you can assume the temperature everywhere in all the world, everywhere is around 20 degrees. Or assume 10,000 degrees, it doesn't matter, because we call it initial value. Assume 6,000 degrees. But after a few hours, the answer will converge and your data makes sense, okay? Therefore, for curiosity, put 65,000 degrees, okay? Temperature at every point in the world, put 65,000 degrees. But after simulation, after a few hours, your answer converge and makes sense, okay? Probably might take 2 hours or 3 hours, okay? But now, this effective initial value, it changed the answer for some time. Therefore, you have to run your program for 2 days or 3 days. Therefore, you have to have a loop. You do the calculation for 1 day, and you calculate the second day and third day. And the question here, how do you know that your answer converge? The way you do it, you take a point in the wall, one of the points that anyone you select, and you calculate the temperature when you go to this first day. Let's say you keep the temperature at, let's say, at 4 o'clock in the afternoon, at east wall, whatever it is. Keep that temperature somewhere and compare it with the temperature tomorrow at the same time. If the difference between the temperature today that you calculate and the temperature for tomorrow is less than 0.5 degree, you can mention why answers converge. If not, you have to continue, okay? Therefore, please start to do it because we need some discussion next Tuesday. The only time my discussion, what I'm saying, makes sense to you when you go through your program, okay? This will take some time. It's not as easy as the first one. The first one was only a simple assignment, but this one, you need some try and error to find what exactly going on in your program. Because we call it here is initial value. Therefore, when you start your program, you have 30 equation, you have 30 nodes, you do not know 30 temperature. You can select those 30 temperature initially, each of them is 65,000 degrees. And then solve it, and then you see what will happen. Any question, please? Any question? Therefore, please start to do this part of the project. I know your midterm is coming soon for all of your courses. Please start it today or tomorrow. And at least we have some discussion on Tuesday that I can be able to answer you. My explanation, the only time makes sense to you if you start to write your program and you see what will happen. Okay, therefore we mentioned here that you have to keep track of the thickness of the wall and the difference between implicit and explicit. If you go explicit, you have to calculate all this coefficient of this temperature for that node and make sure this is always positive. Okay, therefore I do not recommend because it may take a lot of time. Okay, look at here that you have, in this case, that example, your textbook mentioned here, you have one node here, one here, and you mentioned to calculate from here. You can see your delta x, delta t has to be less than 15 seconds. Okay, it has to be less than 15 seconds to satisfy this equation. To satisfy this equation, in order to satisfy this equation, it has to be something 15 seconds. Okay, therefore these are, you have to do the calculation. Okay, therefore here mentioned this term has to be positive, and therefore that's the requirement. Any question, please? Okay, these are the solutions that you mentioned in your textbook. Therefore, I will stop here, and I encourage you to study your project as soon as possible, that I can help you next lecture. I will be available from 2 o'clock, but if you have any question, you can ask me.
Sir?
I'm sorry. Yes, sir.
Someone in the chat is asking if we're gonna get the grades back from project 1 before we submit project 2, so we can correct our mistakes.
Okay, somebody asked. Okay, chat, because I'm.
Yeah, it's okay.
No, my screen does not allow me to look at my chat because of.
Yeah, that's what I'm saying. It's okay. We know that you can't look at the chat at the same time.
Because yes, yeah, I will try to explain the TA how to mark it, but it doesn't matter what mark you get here. The question here, the second part is absolutely independent of the first one. We try. Again, my friend, you know, everybody has a lot of excuse these days, because they're sitting and working at home. I will encourage my TA to give it back to us as soon as possible. I will try to have a Zoom meeting with him this evening or tomorrow and explain to him how he's supposed to mark. And probably I have to meet him again because we'll see how exactly it's done. But we try to hand it in as soon as possible.
And Professor, are we allowed to have like a meeting with the project marker if we have any inquiries about the project 1?
You know him, you know his email.
Yeah, I emailed him and he said he's not sure if he's allowed or not, and asked me to ask you, and then
yeah, because as I mentioned, I have not met him because he had other problem. I'm trying to arrange a Zoom meeting with him and ask him, but he's going to discuss it with you. He has all the power to discuss it with you, to negotiate with you, to whatever. He's the boss.
okay. Thank you.
Any other? How is the TA? How are the TAs?
Good.
Are you happy with them? Please mention if you need any help now. Don't come at the end of the lecture and start to send me emails. The professor was nasty, the TA was worse and nasty, and so on and so on. Okay? If you need any help, we can help you now. Otherwise, work hard. Okay then, I will stop here now. If you have any question, the only thing I want just to cover the transient part, and our next lecture we can give you more detailed question, but my suggestion to use implicit technique, and this you will not have to be worried about the time. But if you are curiosity, you can do that. Definitely you can use even explicit, but the only thing we have to make sure, if the time step is less than 1 hour, and therefore you have to, because over there's a compromise. If you look at the equation carefully, there's a compromise between time and the thickness, okay? Because you have to select a certain thickness to satisfy that equation, okay? If you look at here, this equation depends on the thickness. If your thickness becomes smaller here, right here, you have the delta x here, the delta x here, okay? Therefore, you become the delta to dictate how much should be, okay? If you look at here, your delta t here that you have here, so is again has to satisfy, and you have to make it select a certain delta t to satisfy this one here. Okay. Therefore, that's the place that you have to have some constraint. Therefore, you have to calculate for every type of the material, for mud, for stone, for other material that you selected for the roof, to make sure that satisfy those equations. And also make sure to see this select a delta x to satisfy that equation. And probably you have delta x has to be very, very, very small to do that, okay? Any question?
Sorry, Professor.
A little louder, please.
Can you send us the solutions for chapter 3 and 4 for the weekend, please?
I will send you for chapter 3.
Okay, thank you.
Then, but the 4, I would like to make sure that at least you open your textbook, you start to chapter 4. Chapter 3, definitely I will send it immediately for you, plus also the time for next lecture. But chapter 4, I will wait at least you get to chapter 4. I will send you to chapter 3 with understanding that, yes, you open chapter 3. The idea here is I would like you to start to learn and develop some confidence. Anyway, the lecture is over. I'm on here. If you have any question, please do ask. But please, next lecture, make sure that you have written your question, equations, and if you have any question that you can ask me. Okay? Because some of you send me your equation the last moment, and I have no idea what it look like, because there's an equation. I do not know what is your layout. I do not know what is your discretization and so on. Therefore, for me, not better to answer. Okay? When you write, make sure that you mention how you discretize the wall and what type of material that you have. Suddenly you have a coefficient of C1, C2, and I have no idea. You ask me is correct or not. I cannot answer those type of questions, okay? But you can approach the TA and you can approach the marker, and if you have, I'm also here to answer your question. Thank you very much. Have a great evening. And I'm here if you have any question.
Thank you, sir. Have a good evening.
You too, dear.